Another type of stress and strain that we'll see is shear stress and strain. A shear stress is a sideways pressure acting on a member. So again, imagine we have a bar or a beam here. It was originally vertical. We have a force being applied, but this is a shear force, a force that is sideways, a force that is parallel to the cross-section of the beam. And so this parallel force pulls the top of the beam sideways and gives us a shear deformation, a deflection from the original orientation of the beam. And so that shear stress, this is a small tau. A small Greek tau is our shear stress. That is still a stress, it's still a pressure. It is the force being applied per area, the area there of the cross-section of the beam. A shear stress is still a stress. It's a pressure that's measured in pascals. A pascal is a Newton per meter squared, or it could also be measured in PSI. When we want to measure the deflection, we don't look at the total distance that the top of the beam is pulled to the side, but rather we're looking at the angle of lateral deformation, the angle between the original orientation of the beam and the new orientation of the beam. And that angle is approximately x, the deflection, divided by L naught, the original value. This is a unitless quantity. This is a distance divided by a distance, but as an angle, we recognize that this is a radian angle measurement. Our shear modulus is the proportionality constant for this shear stress and strain. This shear modulus is also called the modulus of rigidity with a capital G. You'll see that in your engineering courses. And it assumes equal and opposite forces acting across the member. So we looked at one force acting parallel to the cross-section, and there'd be another force acting at the other end, so that these two forces cancel each other out. There's no net force making the member move. There's just a net torque, we'll see, that is causing the top of the beam to be deflected. And so our equation is the shear stress, which is our force over the original cross-sectional area, that is proportional via the shear modulus S, that's our constant of proportionality. This is proportional to the angle of deflection, which is the total deflection x divided by the length of the original beam. The way that we're getting this angle is using the small angle approximation. For very small angles, an angle measured in radians is approximately equal to the sine of the angle, which is approximately equal to the tangent of the angle, and the tangent of our angle here is opposite over adjacent. So that's how we're getting that expression for gamma here, our angle of deflection.